The theory of relativity predicts that the presence of a mass deforms space-time so that particles bend in towards that mass. It's hard to find a place where this effect is stronger than a black hole. In fact, this effect is so strong in black holes that when an object crosses into a black hole, it's said to have passed the point of no return, with its only possible direction of travel being deeper into the black hole and closer to its mass. Now, one of the things that makes black holes so cool and so powerful is the fact that their entire mass is condensed into this infinitely dense and infinitely small point known as the singularity. Even though we don't know exactly what goes on there, scientists have a pretty good idea that when an object reaches the singularity, it's crushed down to infinite density, and its mass is added to the total mass of the black hole. The intense gravitational pull of the singularity is known to be so strong that nothing, not even electromagnetic radiation such as light, can escape a black hole. Given that it has the ability to trap light itself, it's not that surprising that black holes can do some pretty weird things to the objects that fall into them. As it crosses the event horizon, the end of the object that's closer to the intense pull of the singularity is going to experience that gravitational force sooner than the other end does, and this results in the object being stretched out on its way down. The gravitational pull of the singularity can have a similar effect on light too, as it stretches out the wavelength of the light that reflects off of the object as the object is falling. This makes the object look redder as it nears the singularity in a process known as gravitational redshift. So not only can black holes warp space and light, but they can also in a sense warp time. To a distant observer, a clock would appear to be ticking more slowly closer to a black hole than it would farther away. This is an effect known as gravitational time dilation, which essentially means that the stronger the gravity and its effect on space-time, the slower time is in that region. So as I mentioned earlier, it's widely believed that nothing can escape the vicinity of a black hole once it crosses the event horizon. That's not entirely true though. Studies suggest that electric currents around rapidly spinning black holes can twist magnetic fields into forming powerful jets of hot plasma containing positrons and electrons, which are shot out of the event horizon. Quantum field theory suggests that some tiny particles like neutrinos can make it out of black holes through quantum tunneling on a subatomic level. Also, according to quantum field theory, black holes emit Hawking radiation, by which subatomic particle pairs are broken up so that one particle gets shot out of the black hole. So you can escape a black hole if you're a plasmablast or a subatomic particle. By the way, Hawking radiation eventually ends up being the ultimate death of the black hole, because every time those little particle pairs break up, the one that's left inside the black hole is left with a net negative charge, which reduces the overall charge of the black hole and weakens it. Eventually, the black hole radiates itself out of existence. Needless to say, space warping, time-bending astrophysical phenomena that spit out plasma and engulf everything open up a whole bunch of very interesting research questions to explore. Only further study will be able to answer all of the unanswered questions about them as we continue to unlock the mysteries of the universe.